Title on dynamic witnesses for static type errors.
All right, thank you. My name is Eric Seidel. This is joint work with my advisor Ranjit Jalla and Wes Weimer. So the title is Dynamic Witnesses for Static Type Errors, or perhaps ill-typed programs usually go wrong. So here's a function that one of our undergraduates wrote at UC San Diego. It's supposed to sum a list of integers. Unfortunately, there's a type error hidden away in this program, and if you ask the OCaml compiler, it will say the type error is in the recursive call to SumList, because SumList returns a list, and yet we were using it here in the context where an int was expected, so that's no good. Of course, a lot of us would probably look at this and say, well, the error is actually in the base case where we returned the empty list instead of 0. But on the other hand, the recursive call is related because that's where the int constraint is coming from. So perhaps we should highlight both of these expressions and kind of slice out a relevant portion of the program. And you could even go a step further and draw a data flow arrow showing how the empty list flows into the recursive call. But in this work, we're going to take a completely different approach. The idea behind a type system, right, is that it should exclude bad executions from happening. So ideally, if there's a type error, there should also be a bad execution. And if that's the case, then why not just find the bad execution and show it to the user? And it just so happens that we're in luck here because SumList does have a bad execution if we call it with the input list containing 1. And if we do that, we start evaluating it, we'll eventually reach the term 1 plus the empty list, at which point we're stuck because, of course, you can't add an integer in a list. So what I'd like to argue for here is that, if we can, we should provide a dynamic witness that the user can interact with, rather than blaming a single static location or a set of static locations. So the rest of this talk is going to be split into 3 sections. First, we're going to talk about how do we actually go about finding these witnesses. Second, we're going to see how we can visualize these witnesses in a nice interactive debugger. And third, we'll evaluate the approach and see how it actually works in practice. So if we want to find witnesses to type errors, let's first make our job easier and pretend that all functions take a single input, and then we can see how to generalize the approach to functions of many inputs. Now, the idea is that we want to search for an input that will cause the program to go wrong. So the immediate question we should be asking is, what types of inputs should we be searching for? We can't just search for arbitrary inputs of arbitrary types, because if we did that, then we might decide that, well, true is a witness to the type error in SumList, because if you call SumList on true, we'll chug along and reach match true against these 2 list patterns, at which point we're stuck because you can't obviously match a Boolean against a list. But no one here would accept that as a valid witness, right? Because basically the problem is that it's getting stuck too early. The intuition is that, if we replaced true with some other value, for example, a list, we could keep making progress along the same execution path. So the idea underlying our search is going to be that we want to be as lenient in the search as possible. And the way we accomplish that is by borrowing the notion of holes from small-check, which allow us to represent unknown inputs. In particular, in our case, we don't even know the types of these inputs. We then proceed to explore the executions of the program. We're finding the holes on demand once it's become clear from the context what type those holes have to have in order to keep making progress. And the result is that we get a search procedure that generates lenient inputs that allow the program to progress as far as possible before it finally gets stuck. So let's see how this looks in practice on our friend the SumList function. We start off calling SumList with a fresh hole, which I'll call $x's. And we take a single step forward, and we reach match $x's against the 2 list patterns. Now, at this point, we know that $x's must be a list of some sort, because that's the only way we can keep making progress. So we have to pick either the empty list or a const cell. And perhaps we pick the empty list first. Well, in that case, we just go into the base case, return the empty list, and we're done. So that wasn't very interesting. Let's backtrack and try the other branch. In this case, we're instantiating $x's with a const cell that has two fresh holes, $y and $y's. And we go ahead into the cons branch and get to the expression $y plus SumList of $y's. Now we have this recursive call with $y's. We can make progress on that. And we can go forward to match $y's against the same two list patterns. Again, we know that $y's must be a list of some sort, so perhaps we instantiate it with the empty list as before, and we get to $y plus the empty list. Now, we'd really like to make progress on the plus expression, but we need a concrete integer on the left in order to attempt that. So we'll go ahead and instantiate it with perhaps 1. But now we're in trouble because we've reached 1 plus the empty list, and we can't make any more progress because, of course, you can't add an int and a list. So this is now we've actually found a nice witness, and we can go ahead and clean it up a little bit by substituting the instantiations of the holes back into the original trace, and we get this trace. Of course, this is kind of verbose. There's a lot of stuff going on. So we might take one more step and abstract over some of the details of the trace to what we call a jump compressed trace, where each of the arrows abstracts over possibly multiple single-step reductions forward to the next function call or return. So in this case, we were able to find a good witness to the type error in SumList in the form of the list containing 1. But the question is, can we do that in general? So in the paper, we prove a theorem that says that yes, we actually can do this in general. And specifically, it says that if we find a witness, then for all inhabited input types, there exist values of those types that will make the function go wrong. And you can see the full details of the proof in the paper. So that's how we find witnesses to functions of single inputs. Of course, we'd really like to be able to apply this technique to functions of many inputs. And you might be wondering, why are functions of many inputs even a problem? The answer is that in a higher order language like OCaml, I could have rewritten SumList like this in terms of fold left, and then eta reduced the parameter away, so it appears syntactically to not take any arguments. And since we haven't type checked the program, we don't have the benefit of the typing information. And if we just naively executed SumList on its own, we would get to this lambda term, and we're done. Unfortunately, we're at a point here where evaluation is not stuck. In fact, it's terminated normally. But there's a type error hidden underneath the lambda that we just can't reach. So there is actually a question here of how many arguments should we supply to the input term. Luckily, it's an easy question to answer. We can just keep supplying new arguments to the input term until the evaluation, until the term reduces to something other than a lambda. For example, if we just supply a single argument here to SumList, we'll get to the lambda term we were at before, except now we have this argument at the end, so we can actually apply it, and we can keep chugging along until we find an actual type error in the 1 plus the empty list inside that fold list application, fold left. So that's how we can find witnesses to type errors. Now, given that we have a witness, it would be nice if we had some way to interact with the witness and provide a nice visualization and perhaps a debugger on top of it. And so that's exactly what we've done. We built a tool that we call NanAmelie that allows you to search for these witnesses and then debug the resulting execution. And we've been using this in our courses at UCSD for the past year or so. So the way this works is on the left we have an editor pane that's loaded with our SumList function. And on the right is going to be the interactive visualization of the execution. We can go ahead and load it up by clicking the check button, and we see it's found a witness SumList with the list containing 0. So the visualization starts off with the input term, in this case SumList of the list containing 0, and you might notice when I hover over it, it pops up a little environment box that shows us the current environment at that step in the computation. And the other term that's on the screen there is the stuck term, 0 plus the empty list. And there's a thick arrow connecting the two, which represents that there are multiple evaluation steps happening on the path from the input term to the stuck term. I can select one of the terms, like the input term, and some of these buttons up at the top light up, that allow us to implement some of the standard debugging steps that we might want to use. For example, we can take a single step forward, but we can also take a big jump forward, head to the next function call or return, which is what we're going to do here. That inserts a new term, 0 plus SumList of the empty list. You notice here the term is pre-selected, and we've highlighted the current red X and faded out the rest of the context so that the user can see where computation is going to happen next. And we also highlight the corresponding piece of the actual code in the code editor. So at this point, we've selected 0 plus SumList of the empty list. This is somewhere in the middle of the computation. And so since we've collected the entire trace already, we can easily take a step backwards in addition to stepping forwards. The other thing we can do at this point, since we're sitting at a function call, is we can step into that recursive call and isolate it and just look at that individually. And if we do that, it will pop out a parallel trace that shows that SumList of the empty list reduces down just to the empty list. But we don't actually need that in that case, so we'll just undo that and come back to our jump compressed trace. Now at this point it's very clear that if you provide SumList with the empty list, it reduces to the empty list, which should really set off some red flags, because SumList really ought to return an integer and not a list. And so that should draw our attention to the nil case in the definition, and we can see, of course, that's just returning the empty list directly. And now we've identified the problem, and we can take action to fix it. So that's a brief overview of this interface that we've built. It works very nicely for debugging type errors. It also turns out to work quite nicely for just showing how the evaluation of OCaml functions, well-typed or not, work. So next I'd like to take a look at some more interesting examples of ill-typed functions that we've also drawn from our undergraduate students. First off, we have a function digits of int, which takes an input n and is supposed to return a list of integers where each integer in the list is a digit of the input. Unfortunately, the student has written this helper function they called append, which is really doing a cons instead of a list append. And then they've used it inside digits of int. But the append helper function type checks on its own. So the OCaml compiler says, OK, this is fine. It has the same type as cons. We'll use that later. And then it goes into digits of int, and it looks at the call site to append, and it sees that, well, the first argument is digits of int, or a call to digits of int. We know from the base case that digits of int returns a list. Therefore, the second argument to append must be a list of lists. And yet, the second argument of append is clearly a list of ints. So we should blame the integer expression there because that's where we detected the error. On the other hand, on the right-hand side, we have our jump compressed trace from NanAmelie that shows very concretely how if you just call digits of int with the input 1, it'll eventually turn along to append of the empty list and the list containing 1. And if you go a little bit further, you'll reach the empty list cons the list containing 1, at which point you're in really bad shape because you can't cons a list onto a list of integers. Lists have to be homogeneous. The next function I'd like to look at is a function we call WWhile, which is essentially a functional while loop. It takes a function and a starting value, and the idea is you keep threading values through the function until the second element of the tuple it returns is false, at which point you're done. Again, this function type checks on its own, and so the OCaml compiler keeps on going, and eventually it gets to the call to WWhile, with the argument f, which is actually a function and not a tuple, because the problem is that inside WWhile, the student has forgotten to call the function f at all. It's just matching f directly against the tuple patterns. So the OCaml compiler decides, well, f must actually be a tuple. And again, then ends up blaming the call site to WWhile. Whereas on the right-hand side, again, we have one of our traces, which shows that if you just try to evaluate this expression, WWhile of f and 2, you'll eventually reach a point where you're trying to match this function value against a tuple pattern, and you can't do that. So the common theme here is that the static view of that the OCaml compiler is providing can end up misleading the user, whereas our traces provide, first of all, a more holistic view of what actually went wrong in the computation. And second of all, it provides an interactive debugging environment that you can actually explore the computation in and come to your own conclusions about what's going on and what needs to be fixed without focusing the attention particularly on one place or the other. So that's how we visualize the witnesses. Next, let's take a look at how well this technique actually works in practice. For this, we wanted to answer 3 questions. First of all, do these witnesses even exist? We all know that type systems are conservative, so there must be some programs that are ill-typed but don't go wrong. Second of all, are the witnesses simple? And lastly, are the witnesses actually helpful in trying to diagnose and fix these type errors? To answer the first 2 questions, we looked at a set of 4,500 ill-typed programs taken from students at UC San Diego and University of Washington. The programs encompassed recursion, higher order functions, polymorphic data types, all the sorts of things you would expect to find in a introductory functional programming course. These were student programs, of course, so they were on the small side. The largest one was around 300 lines of code. So to answer the first question, do witnesses actually exist? We checked all the programs, and we found that for 87% of them, we can find witnesses in 10 seconds or less. And if you restrict yourself to 1 second or less, we can find witnesses for, either 79 or 85% of them. And I point out the 1 second boundary because that's kind of on the order of what you could integrate into your edit, compile, debug cycle. So this is actually something you can kind of use interactively. The other interesting side note is that while the vast majority of the witnesses that we found did actually lead to a type error at runtime, some of them, like about 4% in both cases, actually led to an unbound variable error before we could reach a type error, and yet others simply diverged before we could reach the type error. Second of all, are the witnesses simple? So for this, we examined the jump compressed traces that we produced and looked at the length of the traces. And what we found is that almost 60% of them have 5 or fewer jumps, and just over 80% have 10 or fewer jumps. So this is kind of in the range of what might reasonably fit on a screen and give you a reasonable first overview of the execution, at which point you can then take individual steps to look at specific details. Lastly, we want to know, are these witnesses actually helpful in diagnosing and fixing type errors? And to this end, we did a user study with undergraduates at the University of Virginia who were enrolled in a functional programming course where they were learning OCaml. As part of one of their exams, we gave them 4 ill-typed programs, which we extracted from the UCSD dataset. In fact, we've already seen 3 of the programs. And we asked them to explain and fix the errors. And then we split them into 2 groups per program. And group A was given OCaml's type error message, and group B was given our jump compressed trace. Since this was done in the context of an exam, it was all on paper, and it looked something like this, with group A on the left and group B on the right. Then we assigned 4 annotators to grade the responses, and what we found is that the students do seem to perform better in terms of providing accurate explanations and valid fixes to the type errors when they're given one of our dynamic witnesses. Though you'll notice that due to the exam setting, there were we could use some more data, especially on the WWhile function. There simply weren't enough students who actually filled out that question as part of the answer, as part of their submission. So to summarize, we saw how to find witnesses to static type errors. We saw how to visualize them nicely, and we evaluated our approach. And what we found is that generating dynamic traces to explain static type errors is first of all possible, and it's both practical and it appears to be helpful, at least in the context of novice programmers. Thank you.
Okay, I have a remark first. So the SumList example can be corrected by fewer keystrokes if you take another type, right? I mean, if you write ++ instead of plus, you get a correct example as well.
That's an interesting point. But I would argue it's not a semantically correct fix.
No, it's only the name
yeah.
it's a semantically correct fix.
Well,
it's only the name that says it's a sum. There's nothing else, right?
Sorry?
It's only the name that says that it's a sum. It could be the append function.
That's true.
Concat.
Yeah.
Okay. Yes.
So in one of your slides you said that... Hello, I'm Eric Crockett. You had a slide that said you found in 5 steps or less and 10 steps or less, you found an example.
Yes.
So I was wondering if you looked at that as an expert, professor, could you come up with an example in fewer steps than what your program came up with?
We haven't taken a very systematic look at that, but a couple of the examples I think I could. Like in fact, even for the digits of int function here, I think the second and third steps there are frankly pretty irrelevant to explaining the type error here. So yeah, I think you could if you were an expert. Oh, yes. Probably, yeah. So one thing that I didn't talk about too much is that in the actual implementation, we use a random instantiation. So there will be cases where we produce larger witnesses than are actually necessary.
John, go for it. John Hughes, Charles Mission Cubic. 2 quick questions, if I may. First of all, when you do this exploration, there's a possibility that you may find other errors, like head of the empty list or division by 0. Mm-hmm. Could you just not tell the students about that because it's not a type error, or what?
No, we would tell them about that too. I didn't talk about that here because what we're interested in, in this case, is mostly finding type errors. But I would include that in other things that we could. Other forms of valuable feedback that we could provide, like there's an unbound variable error, or this program absolutely diverges according to a really simple heuristic. Yes.
So the other question was, there are some things that are type errors, like, for example, if x equals y, then 0, else false, which don't lead to a runtime error unless you put them into a context.
Right.
You thought about maybe synthesizing a small context that shows how a program can go wrong.
So we haven't looked at it from that perspective, but what we do is we actually run this system in a loop, and each time we run it, we take note of the actual type of the inputs and the outputs that we produce. And so if 2 of the inputs and outputs conflict, then we can say, well, here's a type error. But it's kind of difficult to actually visualize that. So your idea of providing a context would be provide for a much nicer visualization, I think.
Phil Wadler, University of Edinburgh. It's great that you actually have empirical data for this, and we need to do this much more often. I was actually kind of surprised by the empirical data, because I would have thought you could find witnesses more often than you do, like 99% of the time, but it's only 87%. So that leads to my question, which is, if we do use this technique, then clearly you must give people the actual type errors as well, because sometimes you won't find a witness to give.
Absolutely.
And so you've not explored, okay, overall, for people dealing with programs as a whole, where 13% of the time this doesn't work, which is better than? to give them something that works some of the time and will speed them up some of the time, or is it better for them to just learn to work with the other system because they'll get those errors some of the time? So that'd be an interesting aspect to explore, I think.
Yes, thank you.
Last question.
My name is Jeremy Wang from Tufts University, and my question is, what do you think the challenges would be to adopt this approach for runtime errors?
For runtime errors?
Yeah.
Like what kind? You just like arbitrary runtime errors, like
Right.
John Hughes was talking about, head of the empty list?
Yes, yes.
So I mean, there are a lot of tools that already apply a very similar kind of a approach to searching for witnesses to runtime errors. Whether you're doing some sort of random search for witnesses or an exhaustive search, like so QuickCheck does a random search, SmallCheck does an exhaustive search up to some bound, and then there are even smarter tools that use symbolic execution to prune the search space much faster. So there are a lot of tools that do that already. I think that the interesting thing here is that we're doing it for type errors, which have traditionally been treated as, if your program has a type error, then don't even bother trying to run it.
Thanks very much.